Hello, my name is Richard David TEDJA. First of all, I would like to extend my gratitude to the examiners, Mr. Imade Muwantara, Sarjana Sains, Magister Komputer PhD, Mr. Robertus Hudi, Sarjana Informatika, Magister Komputer, Doctor of Engineering Insinyur Pujanto Yugo Puspito, Master of Science, and also Ms. Sonia Octavianti, Sarjana Sains, as the Secretary for this opportunity for me to present my thesis titled A Performance Comparison of Load Balancer Algorithm on Virtualized Environment, Case Study on Round-Robin List Connection and Weighted List Connection. The research in this thesis have been presented and published in the 8th International Conference on Information Technology, Computer and Electrical Engineering or ICTC 2021, organized by the Department of Computer Engineering of Diponegoro University in Semarang on September 23, 2021. The conference paper is published in the IEEE Explore digital library and indexed by Scopus. The organizers of the conference have not yet issued a certificate, but I can show you the proof of paper publication from the EDAS conference management system, shown here. First of all, I would like to elaborate the motivation of this research. When we talk about cloud computing architectures, it has to involve some form of workload. So workload is a specific application, service, or other forms of computation that is run on a cloud computing environment. The need for proper workload balancing arises as there is a significant increase on data traffic volume and user demand for computational resources during peak time, which in turn causes resources to be fully utilized and leaving no room for additional requests to be handled. This problem is commonly referred as server overloading. So, a solution to this problem is to implement a load balancer system configured with an algorithm that has the best performance to balance incoming workloads so that there are no overloaded nor underloaded nodes. In practice, implementing a load balancer system with the best performing algorithm enables a cloud environment to make optimal use of its available resources, thus subsequently improve scalability and ultimately reducing response time. So, an effort has been done in previous research to compare the performances of cloud computing load balancer algorithms. However, the results of such experiments are interpreted solely by descriptive observation and may not produce the most accurate conclusions. So this research attempts to fulfill this research gap with the use of data analytics. To obtain the conclusions, a predictive data analytic approach is used to determine a load balancer algorithm with the best performance based on various workload characteristics. Now, the purpose of this research is to compare the performances of round-robin list connection and weighted list connection load balancing algorithms and determine which algorithm has the best performance under various workload characteristics. And for that cause, this research raised two problem formulations. The first one, how does a load balancer perform under various workloads within a virtualized environment? And the second one, what is the algorithm that is the best performance that could be implemented on a load balancer within a virtualized environment under various workload characteristics? The design of this research sets four scope limitations. The first one, load balancer is run within a virtualized environment on Amazon Web Services or AWS. The second, workload is simulated using Apache JMeter. The third, algorithms used are round-robin, list connection, and weighted list connection. And the fourth, captured data is analyzed using data analytics. There are 8 fundamental theories used to support this research, which are theories on load balancing, virtualization, workload, and also the concept of round-robin, list connection, weighted list connection, receiver operating characteristics, and confusion matrix. This flowchart represents the workflow of this research. As an initial stage, a literature study is conducted to observe the implementation of the said algorithms on a load balancing system. Afterwards, a virtualized environment will be configured to be hosted on AWS. Within the said virtualized environment, a load balancing system will be configured using hub proxy in order to conduct experiments. To simulate real server traffic conditions, various levels of workloads will be applied onto the load balancing system using Apache JMeter. The performance results of each algorithm will then be captured and analyzed using methods of data analytics to determine which algorithm has the best performance based on the number of threads received and the rates in which the sessions are received. From the analysis, the conclusion of this research is produced. This research utilizes 3 virtualized environment instances provided through AWS. 2 instances are installed with Apache and function as web servers, while the other one is installed with hub proxy and function as the load balancer. To simulate real traffic conditions, various levels of workloads are applied onto the load balancing system using Apache JMeter. This research used 6 JMeter test plans to simulate different workload characteristics. Basically, the experiment starts with test plan 1, which simulates a very light workload, and then gradually increase up until test plan 6, which simulates the heaviest workload level. The experiment is repeated for all 3 algorithms. As for weighted list connection, the weights are assigned in pairs of odd numbers and even numbers with a range of 1 to 20. Odd number weights are assigned to backend server 1, and even numbered weights are assigned to backend server 2. This table summarizes the results of the experiment and highlights which algorithm configured received the most and least amount of threads, alongside the highest and lowest session receive rates. After the workload testing experiment is concluded, data is collected from 2 sources, which are the hub proxy statistics and JMeter test report. Then we perform data cleansing to remove unnecessary data. So there are 2 datasets involved, which are the train dataset and the test dataset. The train dataset is a collection of data which is used to train a machine learning model. For this research, the train dataset comprises of 3 data tables concatenated into one dataset. The 3 data tables are the experiment results for each algorithm, which are round-robin, list connection, and weighted list connection. So upon concatenation, only variables that appear in all 3 data tables will be appended to construct the train dataset. The variables are algorithm, time, threads received, and session receive rate. The target variable of the dataset is the algorithm. In total, the train dataset contains 3,360 instances of data. The second dataset is the test dataset, which is a collection of data which is used to test and evaluate a machine learning model based on patterns and characteristics that it had learned from the trained dataset. The test dataset must not contain the target variable, but must include all other variables present in the trained dataset. To make predictions, a sample size of 10 instances are sampled randomly from the test dataset. Using the datasets, we perform a receiver operating characteristics or ROC analysis on several machine learning algorithms using the trained dataset in order to construct a machine learning model that is the most suitable to predict the best performing load balancing algorithm. 3 machine learning algorithms that has the highest area under ROC curve or AUC will be selected to be inserted to the machine learning model used for predictions. Those machine learning algorithms are AdaBoost, K-nearest neighbor or KNN, and random forest. The ROC curves for each target variable is shown on the right. The color orange represents the ROC curve for AdaBoost, green represents the ROC curve for random forest, and purple represents the ROC curve for KNN. Here are the confusion metrics for each machine learning algorithm. Confusion matrix shows proportions between the predicted and actual class. It is particularly useful to observe the number of instances that were misclassified and how they are misclassified. As we can see here from the figures, AdaBoost correctly predicted 49.6% of round-robin instances, 39.5% of least connection instances, and 91.9% of weighted least connection instances. K-nearest neighbor only correctly predicted 3.9% of round-robin instances, 5.2% of least connection instances, but correctly predicted 90% of weighted least connection instances. Meanwhile, random forest correctly predicted 24.1% of round-robin instances, 16.8% of least connection instances, and 85.1% of weighted least connection instances. Predictions are done using 10 sampled data instances. From the analysis and predictions that has been done, it is found that AdaBoost predicted weighted least connection as the best algorithm on 8 out of 10 or 80% of instances. Random forest predicted weighted least connection as the best algorithm on 10 out of 10 or 100% of sampled instances, while KNN predicted weighted least connection as the best algorithm on 8 out of 10 or 80% of sampled instances. And finally, we have come to a conclusion that this research successfully compared the performance of 3 load balancing algorithms, which are round-robin, least connection, and weighted least connection. 6 workload test plans used in this research resulted in 6 different workload characteristics. A machine learning model comprising of 3 machine learning algorithms, which are AdaBoost, Random Forest, and KNN, is used to analyze the experiment data. The analysis is found that weighted least connection is predicted to have the best performance when compared to round-robin and least connection. There are 4 key suggestions for further research. The first, repeating the experiment with more web servers resulting in a more diverse variation of data. The second, minimize latency by running the workload simulation tool from within the cloud environment. The third, compare the results from other open source load balancing applications other than Hub Proxy, which is used in this research. And the fourth, compare the performance of other load balancing algorithms apart from the 3 load balancing algorithms studied in this research. So this is the end of my presentation. Thank you so much for your attention, and I will be happy to answer any questions.